Hello. In this video, we're going to begin our discussion on vector operations. And we're going to start by talking about a position vector. So if we talk about the vector v, notice this is a bold v, and when you're writing it, you may want to put this vector notation on top to help indicate that you're discussing a vector. So a vector v whose initial point is at the origin and whose terminal point is off towards the end of this vector at some AB in space is referred to as a position vector if we use these pointed parentheses, or rather angle brackets. And what the angle brackets indicate to us is that we have a x component, this right here would measure A, and a B component vertically, which would measure B. So that's representing the horizontal and vertical components. A is the scalar horizontal component of the vector, and B is a scalar vertical component for this vector. Scalar shouldn't be a new word to you, but a scalar just means a numerical quantity, right? Not a vector. So a vector has magnitude and direction. A scalar is just a number that we are, say, multiplying by. So another term for a position vector could be a vector in component form. The component form of a vector, say here we have vector AC. So we have an initial point A and a terminal point C. And the component form of this vector AC, A, starting at x sub 1, y sub 1, that's my first point, that's why we have those sub 1s there, and then x sub 2, y sub 2, representing my terminal point. The component form is found by just subtracting the x, the horizontal components, as well as the y components. So the component form is really the same notation as position form. It's just two different ways to think about it. The main thing, the difference between component form and a position vector is that a position vector is in standard position here. It starts at the origin. Okay, so when we talk about a position vector, that means it starts at an origin, but it's essentially given with these angle brackets in component form. If we know the initial and terminal point of the vector, we can find the component form, and the component form will kind of simplify some of our calculations for us. So in this example, we're asked to find the component form of CF. C, it originates at the point -4, -3, and then my terminal point is at F, the ordered pair 1, 5. So what that means is the vector CF could be denoted by first subtracting the x components. So I have to go from my terminal 1 minus -4 for my initial, comma, and then we'll go with the same order with our y values, 5 minus -3. And that gives me the vector +5, +8. The component form is the same as the position vector. They're the same magnitude and the same direction. It's just the component form doesn't have to start at the origin. Let's try and visualize this. If I were to plot vector CF, I would start at -4, -3. So here's my point C, and my terminal point would be at +1, +5. So there we have F. So drawing that vector would go in a straight line from C, the initial point, to F. And the components, that says we are moving 5 horizontally and then 8 vertically. Now, if we want to think about that as a position vector, that position vector would have the exact same length and magnitude. So if we start at the origin, 0, 0, and I travel to that point, 5, 8, I'm going to get a vector that is the exact same length and at the exact same angle, just in a different position. It's starting at a different spot. So we've got over 5, up 8, which takes me to right here. So from the origin to 8, you'll notice that vector is the same exact length as CF, and it has the same angle or direction. So these are two equivalent vectors. This is the vector CF in component form. It is 5, 8, and if I'm to plot that component form 5, 8 as a position vector, it would look like this. I have one more definition I'd like for us to talk about, or to essentially restate, because we've already talked about this concept. But with vectors, we refer to that length as the magnitude. So the magnitude, or the length of a vector, if it's given with this component form, so we have a horizontal and a vertical, or an X and a Y component, we don't have to do that difference anymore. It's essentially just the Pythagorean theorem. Remember, we indicate magnitude by using these two vertical bars. So the magnitude of the boldface vector V, and if I didn't have a boldface pen or type, I would put that vector notation above it, is going to be the square of the horizontal component plus the square of the vertical component square rooted. So if we wanted to find the length of that vector we had just found, 5, 8, the magnitude of that vector V, so the magnitude of V would be the square root of 5 squared plus 8 squared, which is the square root of 25 plus 64, or the square root of 89. So the length of that vector we just found is root 89. Both of these vectors measure the length square root of 89.